Good morning. Day one of our remote learning mode. I'm starting class at the regular time, running into some issues, but we've got everything hopefully under control now and moving forward. I've got a new writing tablet on order that's supposed to arrive today, and so hopefully that'll be a little bit better than what's I'm writing with today. But we'll just make do with what we have. So I am recording this meeting. If anyone shows up into the Zoom room, that'll be great. We'll add you in. But this is going to be recorded, so you will be able to watch this lecture later. For Wednesday's lecture, my plan is to produce it in advance so that you can start watching it at any time during the day on Wednesday, and certainly I'll post it as soon as I have it ready to go. The work you need to do this week is complete the homework for 12.5 and 12.6. Today we'll do the lecture on 12.5, going over the concepts, work through a few of the examples, get you started on it. Wednesday, there'll be the lecture for 12.6, same type of thing as when we had physical class meetings. And then Friday, I will be in the Zoom room, and I will, if people are there asking questions, we'll go ahead and answer those questions just like we do in class. And I will record those sessions, so in a sense that'll be better than what we were doing in class, because they'll be available for those who either weren't in attendance or for you to review later. So again, these are all, we're looking to the future and trying to say what's going to happen. And like, I had planned to have a video recorded and a lecture and ready to go, but this transition is taking a lot more time than I had envisioned. So with that being said, let's just jump in here. Still no participants, but the nice part of having things recorded is you can fast forward to a section that you need to be. So, but with that being said, we'll still try to keep moving forward. So I'm going to get into the lecture on chapter 12.5. Let me share the screen here. And let's start off. So we're going to talk about some further applications of the derivative. And we're talking about something called related rates. So let me just give you a little bit of an overview of what we're going to need for related rates. Related rates are rates of change that are related to one another. So what that means is, it'll let me do so. Here we go. What that means is we will have more than one variable. And what that means is that when we get remember the derivative is the rate of change. So with more than one variable, the way we take the derivative is with implicit differentiation. Implicit differentiation. So we'll walk you through a few of these, but let me just give you a brief example here. Most of what we're going to be talking about are rates over time. So there's like this third variable of time that's involved in a particular situation. So if we had, say, a formula, a relationship between, let's just two variables, x and y, there's something. we're going to actually use this in the latter problem that's coming up, where x squared plus y squared is equal to c squared, or we'll put some sort of like a constant. We'll just, in this case, we'll say 81. So what this might be visioned as, it's a triangle, the Pythagorean theorem, right? Where this is a 9-foot ladder, and then the wall is, the height up the wall is x, and here's y. So the questions come as the ladder slides down, how fast is the base changing? So we've got the x value is changing, the y value is changing. So notice that as x goes down, y will go up. So to get these rates of change, remember everything is changing with respect to time. So we'll take the derivative, the implicit derivative of each of these with respect to time. So what's the derivative of x with respect to time? Well, that's 2x dx dt. What's the derivative of y? Well, that's, remember, 2y dy dt. Now what we're missing is we're not taking the derivative with respect to x, we're taking it with a third variable, the derivative with respect to time. So this is a little different than what we did with implicit, because we focus really just on 2 variables, but in these problems, we're actually going to get 3 variables, x, y, and the third variable of time. And then finally, the derivative of 81, it's a constant, that's just 0. Okay, and we're going to see that the problems we're given some initial values, and we're given some to check some value at a particular time. So we will be able to generally, we'll be given one of the rates and one of the variables, and then we're able to check the other one, and then we're able to solve for, say, in this case, how the derivative, the change in y, what is the rate at which y is changing. Okay, I hope this, now this is just sort of an overview. This is how we're going to set it up. Now we're going to go step by step through 2 different examples and kind of get a framework for how to set these types of problems up. But I just wanted you to see what we're doing is something similar to what we've already done. However, we will be using implicit differentiation in a slightly different way. So here's where the explanations come in. Let's see, let's use green. I like green. And let's, for this case, we're going to make it a little bit thicker. We'll make it medium. So when we're talking about rate of change of a quantity, so the rate of change of Q, so Q is some quantity, some amount, and it changes over time. Okay, so then that gives us the derivative dq dt. That's the rate of change. So if we're talking about area, our rate of change is dA dt, right, big A. And if we're talking about a circle, the relationship between the area, the change of area, is also related to the change in the radius. So we have 2 different variables, the radius of a circle and the area of a circle, that are changing really at the same time. And so we're going to be looking at radius as a variable and dr dt, the rate at which that radius changes, that will affect the area. So we're going to look at that as an example. And here we go. So here's the example. We're given that the radius of a circle is increasing at 10 centimeters. So this here, this is the rate of change, increasing at a rate. It's a rate of change. So this is dr dt, change over time. And then what the question is going to be is how fast is the area changing or increasing when the radius has reached 5 centimeters. So notice we've got a couple initial values. We've got what the radius is at a given time. We've got the constant rate of change of that variable, the radius, and then what we're going to want to know is how that affects the area. So we need something to relate the area and the radius. So we know, so this is kind of going over what I just explained. We're given the radius, the way it's changing, 10 centimeters per second. We are also told the initial value of that radius when it's 5 centimeters, because that's going to make a difference. Okay, so when we've got a rate, just call it the rate of change, really, right? Increasing at a rate, that's a rate of change. We know that's a derivative. Get off the screen. So as we said, dr dt is 10. We picked that out of the question, out of the information. Also from this question, we know what we're looking for is how fast is the area changing. So we're looking for the derivative of the area, dA dt. And we're looking at that specifically when the radius is 5 centimeters. So as we said, we're looking for dA dt when the radius is 5. So what we're going to need to do is come back to our knowledge about geometry, come up with a relationship between radius and area. So that's our area formula for a circle. So what's the related rate? Well, we start with the area of a circle formula. Area is equal to pi r squared. The way we relate the related rates is we use implicit differentiation. Both of these are changing over time. So they're changing with respect to time. So what's the derivative of A? Well, that is dA dt. Pi is a constant, so it's really just 3.14 times r squared. What's the derivative of r squared? Well, that's going to be, the 2 will come out front, and usually we'll list this as 2 pi. So that's the exponent coming down. Subtract 1 from the exponent. 2 minus 1 is 1. And then what we have is, what is this? This is the derivative of r with respect to t. Now, there's no t variable here because time is sort of like this third variable outside that isn't really part of this formula, but is part of the question. So this is the formula we have, the relationship between the change in area and the change in radius. Now, if you remember, we have the change in radius. So we're going to plug in 10 centimeters per second or per minute. I can't remember. It'll tell us shortly. We were given the radius at a particular time. We were told to check when r equals 5. So notice this will become a number, r will become a number, 2 pi is already a number, and so we will have the rate of change for the area. It'll be just as straightforward as that. Okay, so I'm going to erase this now, and we'll let the system, we'll let the PowerPoint confirm what we already discussed. So we take the derivative of both sides with respect to time. So that's exactly what we did, and use the chain rule. So this is what we had. Remember, derivative of A is dA dt, derivative of r, the 2 came down, so it's 2 pi r dr dt. And then now it's just a matter of plugging in the values we've already got. The rate of change of the radius is 10. So we've got that here. and R is 5. So we plug in the 5 for the R, the 10 for the dr dt, do the multiplication, we get 100 pi, which gives us 314 centimeters squared per second. That's how the area is changing, okay? Because 5 is in centimeters, and the units on the rate of change is centimeters per second. So we multiply these, we get centimeters squared per second, okay? And that's a related rate type problem. So what did we do? We started with the problem. We list the related and changing quantities, so we get variables to understand what we're dealing with, right? So these are the variables. Which in our case was area and radius. And we look at how they're changing. We were given information about how the radius was changing, so we could use that. Then we restate the problem in terms of rates of change. So that is where we start thinking about the derivatives, right? That the changing quantities are derivatives. Then the next thing we did is we looked at the relationship. So we pulled up the formula. And maybe we drew a diagram. We'll show you how that's done in the next one. And finding an equation that relates the variables of interest. In this case, area equals pi r squared for the area of a circle. We used implicit differentiation to take the derivatives of both sides of everything with respect to time. And that gave us a relationship between the rates. Start out with the relationship between the variables, take the derivative, and then we've got a relationship between the rates, related rates. Finally, we solve all this. So we take from the problem the initial values we were given. Usually we're given at least one of the rates, and then we're given some particular time, what's going on. We plug those in. We should have everything. We should have a number for everything except for one thing. That's what we're solving for. And do the calculation, and then we'll have our solution. Just like that. Okay. So here we'll go through one example. Now, I did find an example like this on the Khan Academy, and I pasted that link in along with the lecture material. You may want to take a look at that, and because sometimes looking at multiple explanations are helpful. So let's take a look at this, looking at the ABC. Okay, so first, Jane is at the top of a 5-foot ladder. And the ladder starts to slide down the walls. Fortunately, it's only a 5-foot ladder, but it still could hurt. I don't know. I don't like these problems. It doesn't sound real good, but this is what we have. And what we're told is that the rate of change is 3 feet per minute. So I guess kind of a slow way down there, okay? So Jack is on the ground behind her, and my question is, why didn't he hold the ladder? How fast is the base of the ladder moving when it hits him if Jane is 4 feet from the ground at that instant? Which, okay, so what's going on? Let's draw a picture. We've got a ladder against the wall. We know the ladder is 5 feet, and they'll do probably a better picture than I'm doing here. What we've been told is, okay, this is the height, and this would be the base is what they're going to use, right? And what we're going to do is we want to solve this for when the height here is 4 feet. Okay, and Jane's up here, and Jack must be somewhere over here. And, he should have been watching the ladder and holding it. That's what I say. Anyway, what you can see at this point is the relationship. We've got our variables, right? The height, the base, and this is a fixed quantity. The ladder is not going to change length. So what that suggests is the Pythagorean theorem, where h squared plus base squared is equal to 5 squared. A squared plus b squared equals c squared, right? So that gives us h squared plus b squared equals 25. We're going to want to get this into this is the first step of relating the variables. Now we want to relate the rates. So what we're going to do is, this whole situation is changing over time. So we take the implicit derivative with respect to time. So h squared, the derivative of h with respect to time, the 2 comes down, so we get 2h dh dt. With the b squared, what we get is the derivative of that is the 2 comes down, so we get 2b, and then the derivative of b with respect to time. And what's the derivative of 25? It's a constant, so that is 0. So we're going to be using this, and again, the PowerPoint will spell all this out, but I just wanted to get you through the thought process. And once we get here, what are we going to need to do? Well, remember, they gave us this one. Let's see. So they give us the initial setting of the ladder, that's 4 feet. The height is 4 feet. So we're going to plug in 4 here. We're also told the rate that the ladder is sliding down the wall. That's the dh dt, right? That's the rate of the ladder. And so with no acceleration, it's going to be constant. So that's going to go here. We're going to look for dB dt, how fast that's going. So what we're going to need to do, though, is this is a little different, is we're going to need to plug in, we're going to need to find what B is at this initial stage. So we're going to plug in 4 for H, and we'll get a value for B, so we can plug that in, because right now we would have 2 unknowns. We wouldn't know what B is or the rate, dB dt. So they're going to walk us through that, but we've got our initial values. We'll be able to come back to our relationship to get the value for the variable B at this particular time. And then we'll be able to solve for the rate of change of the base at that particular time. Okay, so, and again, a video, you can always pause, snap a picture if you need to, take a screenshot. There's all these things you can do. If it gets boring, you can fast forward. And actually, there's a little beer thing. I think you can even listen to this at 1.5 to 2 times the regular speed. Okay, so sliding down the wall, changing the quantities. Okay, motion of the base of the ladder. So this is what we talked through. So they're going to get the variables. So they use H for the height of the ladder, B for the base of the ladder, how far it is from the wall. The rate of change of the height of the top of the ladder is 3 feet per minute. So just dH dt. We talked about that. That was part of the problem, stated in the problem. Okay. The rate of change of the distance of the base from the wall, that's what we are looking for when it is 4 feet from when the ladder is, the top of the ladder is 4 feet from the ground. Okay, so that's what we set up. So dH dt, oh, I forgot. You're going to put in -3 because it's going down. It's decreasing, right? Little things, but important things, right? Because we're going to need that. So the question is to find dB dt, the rate of change of the base when the height is 4. So here's our picture. And what we get to do here Make this a little thinner. So this height is, we're going to look at when it's equal to 4, right? And what you know, from Pythagorean theorem, you might say, well, if this is 4, that's 5, this has to be 3. We're going to, and you're going to be correct that at this initial stage, this is going to be 3. And then what we want to calculate, we know that dh dt is equal to -3 because it's going down 3 feet per minute. We want to know what is happening to dB dt. And we're going to see that that is actually increasing, so that should be a positive value. Okay, we've got our Pythagorean theorem, like we set up, h squared plus b squared equals to 25, or 5 squared, right? We take the implicit derivative, which we did earlier, so 2h dh dt plus 2b db dt equals 0. Derivative of 25 is 0. So this we set up earlier. And then what we see is we substitute in for what we know. We substitute the 4 and the -3. But as I mentioned, we still have 2 unknown variables. We don't know what b is, and we don't know dB dt. However, we can go back to the original relationship between the variables and solve for b when h is 4. And that's what they're going to do next. So they go back, they put in 4 for the h, right? So you get 16 equals b squared. 16 plus b squared equals 25. Subtract 16 from both sides, you get b squared equals 9. You actually get 2 values. You get a plus or minus b, say plus or minus 3, but they reject the -3 because it is a distance. So it's a positive 3. Come back to our equation, plugging the 3 in for the base. And now we can just solve this equation. We add 24 to both sides and then divide by 6. 24 divided by 6 is 4. So that's 4 feet per minute. So the base is sliding away from the wall at 4 feet per minute when it hits jack. And that is the end of the PowerPoint. Now, I do have one of those. Let's see, what time is it? Let's check here. 11:14. We've got about 20 minutes of class time left. So let's do this. Let's go ahead and take a look. I'll get back to sharing the screen. Let's go over a few of the questions to maybe kind of get an idea of how to set them up. So WebAssign. Get logged in. And this time of year I get terrible allergies, so which is not really good at with all the stuff that's going around. But I don't have a fever. I don't have body aches. I am tired, but that's because of allergies. And we'll make it through. Okay. So hopefully you guys are hanging in there health-wise. Let's go to 12.5. Oh, also, just a side note, I did extend, what is it, 12.2 and 12.3 until this next Sunday, give you an extra week, just because I know there's a lot going on. Some of you who may have traveled have already been contacted. Some students are actually on forced quarantine, so they can't get out anyway. That's kind of why we went into this. If you were in an area, you got back here, and now you're quarantined for 14 days, or something else. So anyway, or your travel plans were disrupted, so now you're still trying to get back in. And so we'll work with you. We'll make it work. But what we need is, when you are able to, focus on completing the assignments and learning the information, so that we are ready to take the exam number 2. When we do get back together, or if that's not going to work, we will have some kind of an option for online testing. We got to do something, but I'll let others come up with those options and tell us how we're going to take our next exam. But my hope is that things will clear up, and in 2 weeks we'll be back together again, physically. Okay, 12.5. Let's come here. Let's take a quick view. And I remember seeing this first question off the bat. And remember, these assignments were set up a long time ago, before probably before the coronavirus was even a thing. But here's this one on a Bangkok flu cases, and I didn't go to I was hoping to go to Bangkok over winter break, but I didn't. As some of you may know, I have a second home there. My wife has the home. I get to use it. So anyway, this one you just need to identify which one is the rate, and notice the number is growing by 10 new cases every month. So this is a rate here, new cases. And again, for you, it'll change, but that would be our rate. And the initial value is currently 450. So this is just a problem to get you to set it up and be able to determine from reading something what's the rate and what's the variable. Nothing else more to do with this one. Okay, this one is we're looking at rewrite the statement mathematical notation. Okay, so it disappeared on me. Where did it go? And I hope all this is recording well. That's where, I've already run into a few. Here we go. Let's come back. This one's also set up. So what are we talking about? R is the annual revenue of a company. Q is the annual sales. And T be time. So what's the relationship between revenue and quantity? Keeps disappearing on me. Hopefully it shows up. Oh, here it is. As I'm sharing the screen, we'll just see later. But what is revenue? Yeah. The annual revenue would be the annual sales. Q be the annual sales, and T be time. I guess Q is the quantity of sales, so maybe it's the sales times the price, and usually maybe that's a fixed price. So the annual revenue of the tie-dye shirt operating is currently 7,000, but is decreasing by 8,000 each year. So this is our rate of change of the revenue with respect to time. This is our initial value, it's our initial revenue, and then what we're going to want to find, rewrite the question mathematical notation. What we're trying to find is, we're given dr dt, so what do we need to find? We need to find dq dt. dq dt, okay? So again, getting you to think through these, and hopefully it's making sense. Okay, and we'll just look at a few. Let's see, we're almost done here. So here's a ladder problem. We kind of went through that. This one's just wanting you to set up what we were given and what we're looking for. Okay, so you should be able to do that. Circular sunspot. So again, the area and the radius. It's a radius problem. So we did a similar one to that. And again, I just want you to fill those things in. And now we're going to kind of get you a chance to do some problem solving. Here we're going to do with a volume problem. And what we want you to do is set it all up. We're given an initial rate here. Right, an initial rate, 12 cubic feet per minute. And then we want to know when the radius, how is it changing when the radius is 2 feet. So we've got initial values of 2 feet for the radius, 12 cubic feet per minute for the volume, the rate, not the volume, but the rate of change of the volume, right? And so take it from there. Let's see how you do. This one, question 6, is going to be similar. Okay, we're using the same type of a formula, looking at the rate of change of volume. 7, we're given average cost function. Now, the one thing to go here is we're looking for the average cost, where X is the number of CD players. Weekly production is going to be 5,000 players, and then increasing at a rate of 400 players per week. So that is the X is that. What is happening to the average cost? I think that's all we need. We've got an average cost function. We've got how X is changing. We need its derivative, and we can do all that. Okay. And then we've got this one relating X and Y. So we've got a formula here, a little more abstraction to it. And then finally, they're off the screen here. We've got a problem for you to give a try on computers per household, taking a derivative with natural log of X. Remember, the derivative of natural log of X, just give you a little bit of help here. When you take the derivative of, oops, that's not the one I want. You take the derivative of the, I could do it anywhere, right? Natural log of X, when you take its derivative, you're going to get 1 over X. And again, since we are doing a implicit differentiation with respect to time, we're also going to get dx dt. Okay, so that is the derivative when we take the derivative of natural log of X. Just a little bit of help should get you through this. And then, of course, over here, when we take the derivative of Q, we get dq dt. So let's see how you do. Remember, you can come see me during office hours, hopefully. Let me know if you're having any issues with getting logged in. If it's your computer and such, I'm going to refer you to the service desk because that's not my expertise. And I'm struggling with those, but if I find that a number of people are trying to log in and aren't getting in, it might be something that I got set up. I got the link, and I believe all you have to do is click on it, and you should be able to get into the Zoom meeting. But I need to know if someone's trying to get in and not able to. I got 2 messages from students so far, and they said that they feel that it's a problem with their computer. So I'm going to contact them and see how that works out, and refer them over to the help desk. Other than that, I'm going to stop this recording. I'm going to post it so that since nobody came to the Zoom meeting, or at least, you may have been trying, but nobody got in, it's going to be recorded. You'll be able to watch this and move forward. So 12.5, Wednesday, I'll have something set up for 12.6, and I will be back on the Zoom meetings on Wednesday morning. In between that, go ahead and post any questions you have in our discussion forums in Canvas. And I guess, let me do one more thing. We got a couple minutes, right? Share the screen. See this, I come back here and we'll come back to discussions. And, you can add a discussion for chapter 12 and post any questions that you have here. Travis is monitoring the discussion forum. I'll take a look as well, but we'll get your questions answered that way. So have a wonderful day. Keep making the progress and keep in touch. Take care, and I'll talk to you later.